Hey, welcome back. This is CHEM300, and we're continuing Chapter 8 today with talking about mass-to-mass conversions. So our goals in this section are to use the coefficients in a balanced chemical equation and the molar masses of the substances to convert from the mass of one substance in a chemical reaction to the mass of another substance in that same chemical reaction. So this is where we're going to be starting with, say, a given amount of reactant in a chemical reaction. And we're going to use the molar mass of that reactant to convert from grams of reactant to moles. And then we're going to use the balanced chemical equation to convert from moles of that reactant to moles of one of the products. And then use the molar mass of the product to convert to grams of product. And we can go through this type of conversion with any two substances in the chemical reaction. We can go from mass of a reactant to mass of product, from mass of product, back calculate how much reactant we need to make that amount of product. Or we can even say if we want to react 5 grams of reactant A, how much reactant B do we need to react with that? So let's do some math. Let's do some of these. So some key concepts about stoichiometry to remember from our previous lectures. A chemical equation contains conversion factors between the moles of reactants and moles of products. So once you balance your chemical equation, those coefficients in the chemical equation can be used as conversion factors to convert from the amount of any one substance in a chemical reaction to the amount of another substance. So the coefficients represent both the number of molecules and the molecule ratios in the chemical reaction, as well as the mole ratios. And as I've mentioned before, we don't weigh things out in the chemical lab. We don't count things based on the number of molecules or even the moles of substance. When we're working in the real world, we usually use mass. And so we're going to be using molar masses to convert from mass of substance to moles of substance. And then once we have the moles of substance, we can convert to the moles of any other substance in that same balanced chemical equation. So given moles of A in a reaction, we could use the molar mass of substance A to convert to moles of A. And then we could use the ratio from the balanced chemical equation to convert that to moles of B, another substance in that same chemical reaction. So moles are going to be central to all stoichiometry calculations. If you start with a volume of substance, you can use the density to convert to grams. You could convert grams to moles using the molar mass. Then you use the ratio from the formula or balanced reaction to convert to moles of your other substance. Use the molar mass to convert to grams of that substance. You have the density, you can convert to volumes, every which way. Whether you start with number of particles, volume, grams, anything kind of, you end up going through moles as the central point of these stoichiometric calculations. So I hope in this section you start to connect the dots. You're like, oh yeah, that's why we had to spend time learning about moles and learning about molar mass and learning about how to balance chemical equations. Because in Chapter 8 is where all of that starts coming together in what we call stoichiometry in chemistry. So we're going to do 5 example problems in this section to illustrate kind of bringing together what we've already learned about moles and molar mass and balancing chemical equations to start with the mass of any substance in the chemical reaction and convert that to the mass of any other substance in that same chemical reaction. So I'm going to switch over to using a whiteboard. The 5 examples I'm going to do are the same 5 that are in the slides, so you can follow along and work them out as we go to work them out along with me. So let's jump over to a whiteboard here. Okay, so here we go. We have that. Example 1. So how many grams of product will form when 2.4 grams of magnesium reacts? You can assume there's excess oxygen. So we're given a chemical equation. We always have to check if it's balanced. If it's not, then you need to balance it. So here we have solid magnesium reacting with oxygen gas. And I apologize, the formatting when I copy things over from PowerPoint into a whiteboard, we lose the subscripts, but that's O2. Magnesium reacts with oxygen gas to make magnesium oxide. So we're unbalanced right now. We've got 2 oxygens on the reactant side and we've only got 1 on the product side. So I'm going to start my balancing by adding a 2 here. Now my oxygens are balanced, and to finish balancing this off, I'm going to add a 2 there. Okay, so now we have a balanced chemical equation. So our given is that we have 2.4 grams of magnesium, and we want to find grams of our product. We only have 1 product, so magnesium oxide. Plan. Well, we're starting with grams of magnesium, so we got to start there. And then remember, moles are central to all stoichiometric calculations. So we've got to go from grams of magnesium to moles of magnesium. We can't get anywhere without going through moles. And we've already done this calculation back in chapter 6. To go from grams to moles, we use the molar mass of magnesium. And then we're going to go from moles of magnesium to moles of our product, magnesium oxide. And this is where we're going to use the balanced chemical equation. Chemical equation. So for every 2 moles of magnesium that react, we make 2 moles of magnesium oxide. And then our last step, because this question asked us to find grams of magnesium oxide, is we're going to convert our moles of magnesium oxide to grams of magnesium oxide. And to do that, we're going to use the molar mass of magnesium oxide. Okay, so we've got a plan, so let's start solving. So we start with 2.4 grams of magnesium. The molar mass of magnesium, you just check it on the periodic table. Its atomic mass is the same as its molar mass. So we have 24.30. We can round that to the hundredths place for this class. So 24.31 grams of magnesium for every 1 mole of magnesium. And now we're going to use our coefficients from our balanced chemical equation. For every 2 moles of magnesium that react, we make 2 moles of our product, magnesium oxide. So if we stopped here, we would have calculated how many moles of magnesium oxide we could make, but we want to go all the way to grams. So we need to use the molar mass of magnesium oxide. So 1 mole of magnesium oxide, and we've got to calculate that molar mass. So we're going to take the mass of magnesium, 24.31, plus the mass of oxygen, 16, to get 40.31 grams. Okay, so now we're set up. Let's check our units. Grams of magnesium and grams of magnesium cancel. Moles of magnesium and moles of magnesium cancels. Moles of magnesium oxide and moles of magnesium oxide cancel. And we're just left with grams of magnesium oxide, which is what we were asked to find. So now I'm ready to plug it in. So I do 2.4 times 1 mole of magnesium times 2 moles of magnesium oxide times 40.31 divided by the product of all of the denominators. So 24.31 times 2. And I get 3.9795 moles. And then last but not least, we have to check our sig figs. So we have 2 sig figs here. Our molar mass for magnesium is 4 sig figs. Our mole to mole conversion has infinite sig figs. We have 4 sig figs in our molar mass of magnesium oxide. So there are 2 sig figs is going to be what limits our final answer, since this is all multiplication or division. So we're going to end up with 2 sig figs. So we look to the right, we're going to round this up. So we end up rounding all the way up to 4.0 grams of magnesium oxide. This should be grams. Okay, so that's our first example. We started with grams of reactant, and we used our balanced chemical equation and the molar masses to convert from grams of reactant to grams of product. And we assumed that there was more than enough oxygen. We're going to talk about in the next section what to do if we don't know which one of these is going to be what's called limiting, which one of these runs out first. But for this section, we're going to assume that we have more than enough of the other reactant. Okay, let's do our second example. And so we have an unbalanced equation with a solid aluminum reacting with chlorine gas to make aluminum chloride. So if 0.45 grams of chlorine reacts with excess aluminum, meaning we have more than enough aluminum, how many grams of the product aluminum chloride are produced? So first step is you always want to balance the chemical equation. So I've got 2 chlorides on the reactant side and 3 on the product side. So the common factor between 2 and 3 is 6. So I'm going to turn both of those into 6s. So I'm going to put a 2 here and a 3 here. Now I have 6 chlorides on both sides of the equation. And I have 2 aluminums on the product side, so I need to put a 2 in front of this aluminum here. So now I have a balanced chemical equation. We can start doing the stoichiometry. So we're given that we have 0.45 grams of chlorine gas, Cl2, and we want to find grams of aluminum chloride. So our plan is to go from grams of chlorine to moles of chlorine, right? You can't do stoichiometry without going through moles. So you got to find a way to go from what you're given to moles of that to be able to use stoichiometry to do the conversions across the whole equation. So once we have moles of chlorine, then we can use our chemical equation to convert moles of chlorine to moles of our product, aluminum chloride. And after we calculate moles of aluminum chloride, we can use the molar mass to calculate grams of aluminum chloride. So we're going to use the molar mass of Cl2 here. We're going to use the chemical equation there, and we're going to use the molar mass of aluminum chloride for our final conversion. Okay, so let's solve this out. So we have 0.45 grams of chlorine gas, Cl2. It's a diatomic element. So 1 mole of Cl2 is the mass of 2 chlorine atoms. So make sure you multiply by 2. 35.45 times 2 is 70.90 grams. Then from our balanced chemical equation, for every 3 moles of chlorine that react, we make 2 moles of aluminum chloride. That's this step here. And then we want to find grams of aluminum chloride. So if we stopped here at the red, we'd be finding moles of aluminum chloride. So we have one more step to go. We need to use the molar mass of aluminum chloride to calculate grams of aluminum chloride. So every 1 mole of aluminum chloride weighs a certain number of grams, its molar mass. So let's calculate that. So 35.45 times 3, because we have 3 chlorines, plus the mass of aluminum, 26.98. And I got 133.33 grams of aluminum chloride per every 1 mole. That's its molar mass. So let's do a quick units check to make sure they cancel. Grams of chlorine and grams of chlorine cancel. Moles of chlorine and moles of chlorine cancel. Moles of aluminum chloride cancel. And I'm left with grams of aluminum chloride, which is what I wanted to find. So now I'm going to plug everything into my calculator. Do the same thing so you can check your work as you follow along. And I got 0.56416. We need to, of course, go back and do our final sig fig check. So we've got 2 sig figs in our starting value. We've got 4 sig figs in the molar mass of chlorine. Mole to mole conversions are infinite sig figs. We have 5 sig figs in our molar mass of aluminum chloride. So our final answer is going to be limited to 2 sig figs. So for our final answer, we get 0.56 grams of aluminum chloride. Okay, let's move on and do our third example. So balance the following equation and use it to determine how many grams of copper 2 nitrate are needed to produce 12.3 grams of copper sulfide. And that would be copper 2 sulfide. Okay, so we have sodium sulfide, Na2S, reacting with copper 2 nitrate to make sodium nitrate and copper 2 sulfide. So we need to balance this chemical equation. That's always the first step. So we've got 2 sodiums on the left and only 1 on the right. So I'm going to put a 2 here to balance out my sodiums. Now I've got 2 nitrates on the reactant side and I have 2 on the product side. So that looks good so far. I've got 1 copper on the product side and 1 copper on the reactant side. And I've got 1 sulfur on the product side and 1 sulfur on the reactant side. So everything is balanced by just putting a 2 in front of sodium nitrate. Okay, next we can start making up, solving our problem. So given given that we want to make 12.3 grams of copper 2 sulfide, we want to find how much copper 2 nitrate that's going to take. We'll just rearrange this. We want to find grams of copper 2 nitrate. So we have a target, right? We have the amount of product we want to make. Like if we want to make 20 pancakes, how many eggs do we need? That's the type of problem we're doing. We want to make 12.3 grams of our product, copper 2 sulfide. How much copper 2 nitrate do we need in order to produce this much product? And we can assume there's more than enough of the other reactant. Thinking back to the pancake example, that's like if we wanted to make 20 pancakes and we had only 2 eggs, but 50 pounds of flour and 5 pounds of baking soda, right? More than enough of the other ingredients. We just need to focus on the eggs since they're going to be what kind of limits how much we can make. Okay, so let's make our plan. We're going to go from grams of copper sulfide, that's our starting material, to moles of copper sulfide using the molar mass of copper sulfide. You always got to go through moles. And then from moles of copper sulfide, we can calculate our moles of copper 2 nitrate using the coefficients from the equation. And then once we have moles of copper 2 nitrate, we can use the molar mass to calculate grams of copper 2 nitrate. And that's what we want to find. So let's solve this out. So we're starting with 12.3 grams of copper sulfide. That's how much product we want to make. 1 mole of copper sulfide. And now we've got to calculate the molar mass. How much does 1 mole of copper sulfide weigh? So that's the mass of 1 atom of copper, 63.55, plus the mass of 1 sulfur, plus 32.06. I got 95.61 grams of copper sulfide. Now we do our mole to mole conversion. So for every 1 mole of copper sulfide that's produced, we need 1 mole of copper 2 nitrate. And those are from the balanced chemical equation. For every 1 mole of copper sulfide that's produced, we need 1 mole of copper nitrate. And last step, we need the molar mass of copper nitrate. So 1 mole of copper 2 nitrate, and let's calculate how much that weighs. So I'm going to calculate the mass of nitrate and multiply that by 2, plus the mass of copper. And I get 187.57 grams. We're going to run out of space. We're going to write our answer down below. Let me just triple check that I did my math there correctly. Okay, good. Okay, so now we're ready to check our units. Grams of copper sulfide and grams of copper 2 sulfide cancel out. Moles and moles of copper 2 sulfide cancel out. Moles of copper nitrate cancel out. So we're just going to be left with grams of copper 2 nitrate, which is what we want to find. So plug everything in to your calculators and let's see if our answers agree. And I got 24.13 grams. And I'm going to check my sig figs before I include my units there, just in case I have to round. So I've got 3 sig figs in my starting value, 4 sig figs in my molar mass, infinite sig figs in my mole to mole calculation, and 5 sig figs in my second molar mass. So I'm going to be limited to 3 sig figs. So for my final answer, I get 24.1 grams of copper 2 nitrate. So if we reacted 24.1 grams of copper 2 nitrate with more than enough sodium sulfide, we'd expect to make 12.3 grams of copper sulfide product. Okay, we've got two more examples to do, examples 4 and 5. So sulfuric acid can dissolve aluminum metal according to the reaction below. Suppose you want to dissolve a 22.5 gram block of aluminum. What's the minimum amount of sulfuric acid in grams that you need? And then how many grams of hydrogen gas will be produced by the complete reaction of the aluminum block? Okay, so first thing, right, you've got to balance our chemical equation. So if I start by checking my sulfates, H2SO4, I've got 1 sulfate on the reactant side and I've got 3 on the product side. So I'm going to start by putting a 3 right there to balance out those sulfates. Now I'm going to check my aluminums. I'm going to save hydrogen for last. I've got 2 aluminums on the reactant side, on the product side, so I'm going to put a 2 in front of my aluminums here. Now my aluminums and my sulfates are balanced out. Last thing is hydrogens. I've got 6 hydrogens on the reactant side, so I need to put a 3 here to get 6 hydrogens on the product side. And now everything is balanced. So let's work on part A first. What's the minimum amount of sulfuric acid to react with all 22.5 grams of aluminum? So we want to go from 22.5 grams of aluminum to grams of H2SO4. So if we want to react all 22.5 grams of aluminum, how much sulfuric acid do we need? So we're going to go from grams of one reactant to grams of another reactant. And because we're using the mole ratios, this is going to tell us exactly how much sulfuric acid we need to react with all of the aluminum based on our balanced chemical equation. So we're going to start with 22.5 grams of aluminum. You got to go through molar mass to do stoichiometry. So every 1 mole of aluminum from the periodic table weighs 26.98 grams. And then we're going to use our balanced chemical equation to convert from moles of aluminum to moles of sulfuric acid. So for every 2 moles of aluminum that react, that's from that 2 there, it's going to react with 3 moles of sulfuric acid. Again, from our balanced chemical equation. And it wants grams of sulfuric acid, so we need the molar mass of sulfuric acid. So 1 mole of H2SO4. Let's figure out how much that weighs using the periodic table. So I've got 12 sulfurs. Or sorry, I've got 4 sulfurs. 4 oxygens. Let's just get this right. 16 times 4 plus a sulfur plus 2 hydrogens. And I get 98.08 grams. Make sure you get the same thing. I'm going to double check mine since I started that one off almost having a typo there. So 4 oxygens plus sulfur. So it's 2 oxygens. I got the same thing. Okay. So we check our units that they're going to cancel out grams of aluminum, moles of sulfuric acid. So we're figuring out grams of sulfuric acid. I'm going to plug everything in. And let's compare our answers, see what you get. And I get 122.78 grams of sulfuric acid. And if I go back and check my sig figs, I've got 3 sig figs in my starting given. I've got 4 sig figs in my molar mass, infinite sig figs in mole to mole conversions, and 4 sig figs in my other mass. So I'm going to round this to 3 sig figs. So we end up getting 123 grams of H2SO4. So that's how much sulfuric acid we need to completely dissolve a 22.5 gram aluminum block. That's the answer to A. Now checking B, how many grams of H2 are going to be produced by the complete reaction of the aluminum block? So if we completely react all 22.5 grams of aluminum, how much of the hydrogen gas product are we going to get? So we're going to have the same starting value, 22.5 grams of aluminum. And we want to now calculate grams of H2 gas. So we're going to start with 22.5 grams of aluminum. Remember, you got to go through moles. 1 mole of aluminum weighs 26.98 grams. And now we're going to use our balanced chemical equation to convert from moles of aluminum to now we're interested in moles of hydrogen gas. So for every 2 moles of aluminum that react, we make 3 moles of hydrogen gas from our balanced chemical equation. And last step is to use the molar mass of hydrogen gas to figure out how many grams of hydrogen we make. So 1 mole of H2 weighs 2.02 grams. If we do a units check here, we've got grams of aluminum and grams of aluminum canceling, moles of aluminum canceling, and moles of hydrogen gas canceling to give us just grams of hydrogen gas. Okay, so let's plug everything in. You should be plugging in at home as well to make sure we get the same answer. And I got 2.5268 2.5268 grams of hydrogen gas. And of course, we got to go back and check our sig figs. So we have 3 sig figs in our starting value. We had 4 sig figs in our molar mass, infinite sig figs in our mole to mole calculation, 3 sig figs in the molar mass of hydrogen. So we're limited to 3 sig figs here. So your final answer would be 2.53 grams of hydrogen. Okay, one more example. Let's do one more together. This is example 5. So we're going to write the chemical equation for the reaction between nitric acid and calcium hydroxide. Let's classify the reaction in as many ways as possible, kind of a little review from chapter 7. And then if 2.5 grams of calcium hydroxide is reacted, how many grams of nitric acid are required? And then how many grams of the aqueous product are made in the reaction if we reacted the 2.5 grams of calcium hydroxide? Okay, so first thing we got to write this chemical equation. So we have nitric acid, that's HNO3 aqueous, reacting with calcium hydroxide, calcium, and it's going to take 2 hydroxides because calcium is 2+, each hydroxide is 1-, so we need 2 of those to have this be a charge neutral ionic compound. That's aqueous. And now we're going to swap ions. So it's an acid-base reaction, nitric acid, calcium hydroxide is a base. So one of our products is going to be water. H is going to react with OH to make H2O. Liquid. Plus our second product is going to be the product between nitrate and calcium. So calcium nitrate. Calcium, remember, is 2+, nitrate is 1-, so we're going to need 2 of those nitrates to make this charge neutral overall. And this is going to be aqueous. Anything with nitrate in it is automatically going to be aqueous because that's one of those always aqueous ions. Okay, so we've got our chemical equation written. Now we need to balance it. So I've got 1 calcium on both sides, so I'm going to try to leave the calciums alone. I've got 2 nitrates on the product side, so I'm going to start by putting a 2 here in front of my nitric acid. So now my calciums and my nitrates are balanced. Let's check my hydrogens and my oxygens. So I've got 2 hydrogens in nitric acid plus 2 hydrogens from this OH2. So I've got 4 hydrogens on the reactant side, and I only have 2 on the product side. So I need to add a 2 here as well. Now I've got 4 hydrogens on the product side and 4 on the reactant side. And if I check my oxygens that are not part of nitrate, because I already balanced nitrate, I've got 2 oxygens and hydroxide, and I've got 2 oxygens and water here. So everything is balanced. So now we can start solving this problem. So part A, this is a review from chapter 7. Classify the reaction as many ways as possible. Well, we swapped 2 sets of ions, so that's double displacement. And we reacted nitric acid with the base to make water and a soluble salt, an ionic compound. So that means it's also an acid-base reaction. It's not going to be a single displacement reaction. We already classified the reaction type based on what the atoms are doing. It's not a gas evolution reaction. We didn't make any gas. It's not a redox reaction. It's not a combustion reaction. So these are the 2 ways we can classify this reaction: double displacement and acid base. So let's get to the stoichiometry. So we react 2.5 grams of calcium hydroxide. It asks how many grams of nitric acid are required. So if we know how much calcium hydroxide we're going to add, we want to calculate how much nitric acid we need to add so that they react together completely. So we're starting with 2.5 grams of calcium hydroxide. And we want to go 2 grams of nitric acid. So let's start with our given 2.5 grams of calcium hydroxide. We need to convert that to moles. So we need to figure out the molar mass, 1 mole of calcium hydroxide. How much does that weigh? So we'll use our periodic table to do that. We have the mass of 1 calcium, 40.08, plus the mass of 2 oxygens, plus the mass of 2 hydrogens. And I get 104.72 grams. Now we're going to use our chemical equation, which is now balanced, to convert from moles of calcium hydroxide to moles of nitric acid. So for every 1 mole of calcium hydroxide that reacts, it's going to react with 2 moles of nitric acid. And then to figure out grams of nitric acid, we need to use the molar mass of nitric acid. So we need to figure out how much 1 mole of nitric acid weighs. So we have hydrogen plus nitrogen plus 3 oxygens. I get 63.02 grams. Okay, so if we check our units quick, make sure we set things up. Grams of calcium hydroxide cancels out. Moles of calcium hydroxide cancels out. Moles of nitric acid cancels out. Okay, so let's plug everything in. 2.5 times 2 times 63.02. And then I divide by the product of everything on the bottom. This is all multiplied by 1, so I'm just going to divide by 104.72. And I get 3.008. And if we check sig figs, we've got 2 here, 5, infinite, and 4, so we're going to be limited to 2. So we get 3.0 as our final answer. Okay, so part C asks how many grams of the aqueous product are made if 2.5 grams of calcium hydroxide completely reacts and there's more than enough nitric acid available. So if we react all of our calcium hydroxide, 2.5 grams, wants to know how much aqueous product is going to be made. So we have to correctly identify our phases on our products in order to be able to answer this. Calcium nitrate is the aqueous product. So we want to go from grams of calcium hydroxide to grams of calcium nitrate. So we're going to start with 2.5 grams of calcium hydroxide. We got to convert to moles. So we know already that 1 mole of calcium hydroxide weighs 104.72 grams. And then from our balanced chemical equation, for every 1 mole of calcium hydroxide that reacts, we make 1 mole of our product, calcium nitrate. And last but not least, we need the molar mass of calcium nitrate to be able to calculate grams of calcium nitrate. So let's figure out what that is. We've got calcium plus 2 nitrogens plus 6 oxygens. So I get 164.10 grams. Always do a units check. Grams of calcium hydroxide cancels, moles of calcium hydroxide, moles of calcium nitrate. Okay, so plug things in. Let's see if we end up with the same answer. And I get 3.8 grams of calcium nitrate. I know I'm running out of space there. I rounded that to 2 sig figs based on sig figs in the rest of my problem. I had 2 here, 5 in my molar mass, infinite sig figs in my mole to mole calculation, and 5 in this molar mass. So I had to limit my final answer to 2 sig figs, rounding it to 3.8 grams of calcium nitrate. Okay, so those were 5 big examples. I know that ended up getting a little bit on the long side, but I wanted to show you a bunch of different ways to use mass to mass calculations. Important key concepts to remember is that when you do these calculations, you always have to go through moles. So start with whatever given value you're given and figure out a way to convert that into moles. Most of the time you're given a mass and then you use the molar mass to convert that to moles. Once you convert to moles, you use the balanced chemical equation to convert to moles of whatever substance you're trying to find. And then you use the molar mass of that substance to convert to grams. So it's the end of our mass to mass section. In the next section, we're going to talk about what's called the limiting reactant. I'll see you then. Thanks, everybody.